First of all, I would like to congratulate all the organizers for such a wonderful conference. A lot of learning yesterday, whole day, and today, of course, after the radiology finishes, we continue with the conference. Okay, so I'm essentially going to cover like how the evolution of AI has happened and where does AI fit for us in radiology. So I'll go through the evolution, how it has happened. So our ancestors could use fire with rubbing the stones, and it was ubiquitous. You could available everywhere, but they wanted portability. So that's how matchstick was invented. But every time using the matchstick was a problem, we want to scale it. So then we developed a lighter. So on. So similarly, artificial intelligence also has evolved because of the scaling which was required. We were on moon in 1960, but there was no chat GPT at that time. So they were still working on maths, and the AI used in 1950s is symbolic AI, which is a rule-based AI, and that's how engineering a lot of things happened. The symbolic AI was rule-based, so it was a very knowledge-heavy based thing because you had to encode all the rules yourself. So again, scaling was a problem. So machine learning came. Then there was some problems with machine learning. Every time you had to teach the features. So deep learning came where the learning become a self-learning process, and so on. Foundation model, and now to agentic AI. So this is what I call as knowledge is everything. Now there was a publication in 2017, Attention is All You Need by Vaswani, which led to development of Transformers GPT. But before GPT, we were working through rule-based AI, and it all dependent on the knowledge you yourself coded in it. So the earliest CAD we used was based on symbolic AI. The benefit of symbolic AI is there is no hallucination. If you encode certain rules, and if you ask the same question 100,000 times, the answer is same 100,000 times. So this is also called as determinism. And while the current AI is probabilistic, if you ask the same question to Gemini 10 times there will be some variation in the reply. So that is the problem which is in healthcare needs a big, we need to address it. Because in healthcare, we don't want different reply every time. So I'm working on that, how we can combine probabilistic AI with a symbolic AI. So symbolic AI works with if-then rules. So if the lesion is more than 20 millimeter, if it has washout, it is enhancing, then it is HCC. So this is simple rule. But there was a problem. Suppose you have 10 imaging features of a lesion, and for each feature there can be 3 different states. And if you combine the combinations, 10 into 3 means to the power 3, the combination becomes 59,000. So this was the bottleneck which was felt while using a rule-based AI. So for anything atypical or something new which, because it was not able to learn, it would crash. So that lead to the new development, and that we call as statistical AI or the probabilistic AI or the machine learning, deep learning, what we are doing now. So what is statistical AI? Here, it converts that knowledge into patterns. So it detects those patterns, and based on patterns, it makes predictions. So like a very common example is predicting sepsis in ICU patients. So it learns the knowledge of how to detect sepsis, and then it, you study say 1,000 patient data on it. So it detects some patterns that when the lactate is rising, WBC is rising, so this is a sepsis. So that's how it learns the pattern, and then it predicts that this patient is probably going to go into sepsis in next 4 hours. So this is how a statistical AI works. So the input is data, and you have taught the outcomes based on that data. So data plus outcomes, so it is able to capture these features and make a diagnosis or do a prediction. Now, there was a problem in this as well. The problem was humans had to teach each and every feature. So as I was saying, now you want, everybody was happy with machine learning, but now we wanted to scale it, to take it to bigger projects, more things. So then, engineers started thinking, what should we do next? And another thing, it was found that it is detecting pattern, it is making a correlation, but it is not understanding like humans. So if you give a data of hospital A, which had 90% cases had cancers, so it understands that this kind of data meaning cancer, but it doesn't understand all the nuances like physicians, all the content in it. So if you take this algorithm to a different data where cancer is only 20%, the results will be very bad. So again, you wanted to scale this thing. So there was this problem. So we wanted to scale knowledge. So we created machine learning. Now we wanted to scale these features, and we wanted the machines to learn these features on it themselves instead of humans teaching. So like I have say 1 million radiology images. It will not be practically possible to train every image or extract features. So then came deep learning. So traditional machine learning was image, you extract the features and then make a prediction. But in deep learning, the feature learning becomes automatic. So what you do, in a traditional machine learning, you took 1,000 images, labeled them, and then you trained the model. And then model predicts based on that. But in deep learning, you will say give 100,000 images. The model itself will try to find which are the features and try to correlate on it and then create a prediction. Of course, some training is required there as well. So machine learning, we are teaching the features, but deep learning is learning the features on its own. Now let's talk about perceptron. So this is the first learning machine or the thinking unit which was given by Frank Rosenberg in 1957, and it was modeled on how the human neuron is. So a perceptron is a mathematical formula basically. So these are the inputs, and each input gets weights. I will explain you what are weights later. Then a mathematical formulation happens and an output comes. So the three main things were inputs, weights, and bias. But a single perceptron could work for a simple problem. So to work it on a complex problems, you needed two new things like activation and non-linearity. I'll explain you what that was done for. Now let's understand linear versus non-linear. If I'm using a specific strength of contrast, say for example 350 milligram, 50 ml is 17 grams iodine. If I make it 100, the iodine becomes double. If I make 150, it becomes triple. So this is a linear relation, right? But now let's look at the contrast enhancement in the liver. If I'm giving 20 grams of iodine, the HU is 250. If I'm giving 30 grams, the HU is 330. If I'm giving more, but if you see, the enhancement is not linear like here. So this is called as non-linearity. And in human body, nothing works in a linear fashion. It's a lot of things are non-linear. So activation function was added to teach it the non-linearity. Now, like as radiologists, we see size, we see speculation, or we see contrast enhancement, or a SUV on PET CT, and then we go through that cognitive process and we make a assumption. Now that cognitive process is not linear. Everything is not by a particular formula. So this is what in perceptron was done. Non-linearity was introduced through activation. Okay, I think one slide is missing about weights and bias. Now, suppose you are teaching the perceptron something and you are giving 3 features. So you will tell what matters more. So out of 3 findings, what matters most? Size matters more, or a contrast enhancement matters more. So like my weightage for arterial enhancement in HCC would be more than the size. Washout has a weightage, so we give a weights to that. And bias is something like if it's a cirrhosis, my bias is usually for looking for HCC. A simple example I will give you. Suppose I take an umbrella with me every day when I'm going out of home. So what do I check? I check whether it is a rainy season, whether the UV index is very high. So I give a weightage. So if it's a rainy season, the weightage clouds, if I see clouds, the weight is high. If I see in summer very high sun and UV index, then the weightage to UV index is high. Now what is bias? If it's a summertime, my bias is not to take an umbrella. I'll manage with a cap. But if it's a rainy season, my bias is always I will take an umbrella whether even if today it is sunny, but my bias is so the bias changes the intensity of weight what you are applying. So that is, I think you'll have to read more. It's difficult to explain in 2 minutes. Okay. So perceptron was working fine, but then again we wanted to scale it. We wanted to now give more information. So one perceptron could not do it. So then came multi-layer perceptron, where you had multiple perceptrons connected. So when there are too many, then these becomes like a hidden layers. So there are inputs, and these are multiple perceptrons, multiple layers, and there is a output. So this is what deep learning is. Now coming to radiology. Radiology is more about computer vision. So 2 things. One is computer vision and second is language. Language because computer vision sees an image, extracts the features. Language helps us creating the report. So 2 things are important for us as radiologists: computer vision and language. So the key algorithm which is used in radiology is convolutional neural networks. Now MLP, the multi-layer perceptron, would see images as numbers, but then you could not scale it, and MLP did not have the concept of shapes, edge, texture, when you add a X-ray or a CT image. Then engineers saw how radiologists work. So they look at the edges, they look at the texture, homogeneity, heterogeneity, organ, So based on what humans did and how our visual cortex processes all this information, a convolutional neural network was created. So this you can read. It has a structure, it has convolutional layers, pooling layers, all that. This ReLU thing is the activation feature, which I was explaining. So like when an X-ray image is given to a CNN, it goes through this process. It looks at the pixels, it looks at the edges, texture, it looks at the shape, location, and all that happens in the all the features which are extracted are given to the deeper layers, and then an output is come. Now, as you know, as in medical, we have radiologist, surgeon, pathologist, we have our different roles. So similarly, they realized in radiology also there are a lot of things which we do, and one CNN could not do the everything. So then they created multiple tasks, and each task had a goal, like classification, like whether this is tumor or not tumor. A simple example. So, you know, ResNet is a popular CNN for that. Detection, YOLO, you see it once, it's a popular CNN for detecting something. It is also used when, you know, in traffic cams, when they click a picture, we jump a signal, so that CNN computer vision picks your car number through that extracts. So something what you do in radiology as well. Segmentation is like outlining and defining a lesion. So one of the tasks nowadays radiologists do is segmentation, either for AI training. But example of segmentation is like when I do liver donor evaluation. So we segment the liver out of the body, and then you split into right and left lobe as a digitally. So that is segmentation. Localization is finding where once you have segmented something, then where is the lesion? Lesion is in the, say, left lower lung. So you have different kind of CNNs. Now CNN was doing detection, segmentation, everything. But then you need two things in radiology. One, you want to add a report. And second is your patients are in sequence. Means they had a CT scan 1 month back. They did a chemotherapy. Now they are checking. So there were two problems: adding sequence and adding language. So let's come to this natural language processing. So natural language processing is a subset domain of AI which works like a human language. Now, natural language processing is not new. It used to be there as a rule-based, then machine learning, and now through deep learning also. And we use natural language processing for clinical notes, discharge summaries, radiology reports, guidelines, prescriptions. Currently, most of the NLP now is happening through deep learning mode. What I use in my radiology as a speech to text is not deep learning based. It was like installed 10 years back. But the current natural language processing is happening through large language models. Okay, so now, as we said, there was a problem. Patients don't have scan for one time. They have scans for multiple times. So CNN was looking and extracting the features from the images. But my problem was continuity and language. So then RNN was brought in, recurrent neural networks. So what recurrent neural network did, CNN and RNN would work together. CNN would do the job of extracting the information, while RNN would act like a decoder and generate radiology report, plus it would also add a context, a temporal context. Compared to previous report, the lesion has increased. Now, CNN and RNN were suffering from memory. So again, we wanted to scale. So to scale this for the memory problem, LSTM was created. So okay, then they realized that too much information is being fed, and the model is getting confused. The model doesn't know what is more important. So if you have a cirrhosis HCC report, for us the most key important finding is HCC and maybe one or two other things. So
we have 2 minutes to wind up.
Yeah. So then attention was brought in so that the model could focus on the main problem. From then attention was working fine, so they created transformers. And GPT, what you use, Chat GPT. GPT is generative pre-trained transformer. It is a type of transformer only where it learns on the attention mechanism. So these are now little interrelated only. When you use a transformer for language, it is called as large language model like Chat GPT, Gemini. But these models are have been trained on too much of data, of all kind of data. So now they are also called as foundation model. So they have gone beyond our language model. So these are called as now foundation models. And now we have come to stage of multimodal foundation models where it can read a CT scan, it can check the history, it can check the previous report, it can check the guidelines and then create a report. And it can even reason and generate a new text out of it. So that becomes a multimodal foundation model. So yesterday the conference, this highlight was there that radiologists would now evolve. You would act like as such you are a gatekeeper now, but now you will also process all that clinical information and give a diagnosis and even decide the management. So again, now this all was there, but the workflow was missing since human were still required. So then we engineers come with the agentic AI. And now the next bottleneck after agentic AI is the governance. So governance is something which I am working right now. And yeah, I think I'll cut. Thank you.